In this video, we have an exercise in finding the nth roots of a complex number. For the exercise, we are going to find all the fifth roots of square root of 3 minus I. We first express square root of 3 minus I in polar form. If z is a complex number, then z equals its absolute value times e raised to the power I times an argument of z. If z equals x plus y times I, where x and y are real numbers, then the absolute value of z equals the square root of x squared plus y squared. If an argument of z is theta, then z equals the square root of x squared plus y squared times the quantity cosine theta plus I times sine theta. The absolute value of the square root of 3 minus I is the square root of the square root of 3 squared plus negative 1 squared, so that the absolute value of square root of 3 minus I is 2. Now we find an argument for square root of 3 minus I. The complex number square root of 3 minus I corresponds to the point square root of 3 minus 1 in the fourth quadrant. If theta is an argument for square root of 3 minus I, then cosine theta is square root of 3 over the absolute value of square root of 3 minus I, so that cosine theta is square root of 3 over 2. So the reference angle for theta is arc cosine of square root of 3 over 2, or pi over 6. Since square root of 3 minus I is in quadrant 4, we choose theta to be equal to minus pi over 6. Therefore, square root of 3 minus I equals 2 times e raised to the power I times negative pi over 6. A complex number w is a fifth root of square root of 3 minus I if and only if w to the fifth power equals square root of 3 minus I, or 2 times e raised to the power I times negative pi over 6, or 2 times the quantity cosine of negative pi over 6 plus I times sine of negative pi over 6. Let an argument of w be alpha, so that w equals the absolute value of w times the quantity cosine alpha plus I times sine alpha. Then w to the fifth power equals the absolute value of w to the fifth power times the quantity cosine of 5 alpha plus I times sine of 5 alpha. Here we applied the Morris formula to the quantity cosine alpha plus I times sine alpha raised to the fifth power to get this expression. Recall that the Morris formula says that the quantity cosine alpha plus I times sine alpha raised to the nth power equals cosine of n alpha plus I times sine of n alpha whenever n is a positive integer. So, matching corresponding parts, the absolute value of w to the fifth power should be equal to 2, so that the absolute value of w should be equal to the real number fifth root of 2. We set 5 alpha equal to minus pi over 6, so that alpha equals minus pi over 30. So the first of 5 fifth roots of square root of 3 minus I equals the real number fifth root of 2 that we will simply call the fifth root of 2, times the quantity cosine of minus pi over 30 plus I times sine of minus pi over 30. Up to 4 significant digits, this is the value of this fifth root. We just mentioned that this is the first of 5 fifth roots of square root of 3 minus I. It is a fact that every non-zero complex number, and this includes every non-zero real number, has 5 distinct fifth roots. Going back to pre-calculus, when we would take the fifth root of a product, we often would just apply the fifth root to every factor. And if there were to be exponential quantities such as e raised to the power I times negative pi over 6, we often would just divide the exponent by the index of the radical or by the index of the root. In this case, we divide I times negative pi over 6 by 5 to get I times negative pi over 30. We still need to find 4 more fifth roots of square root of 3 minus I. We rewrite the polar form of square root of 3 minus I by writing out the argument of square root of 3 minus I using a general formula. Minus pi over 6 is just one argument of square root of 3 minus I. Every argument of square root of 3 minus I can be expressed as minus pi over 6 plus an integer multiple of 2 pi. Or every argument of square root of 3 minus I equals minus pi over 6 plus 2 pi times k, where k is an integer. And now we apply the fifth root to square root of 3 minus I, so that every fifth root of square root of 3 minus I can be written in the form the fifth root of 2 times the quantity cosine of minus pi over 30 plus 2 pi k over 5 plus I times sine of minus pi over 30 plus 2 pi k over 5. Since we are looking for 5 fifth roots, we need 5 consecutive values of k. The first fifth root that we found corresponds to k equals 0. When this time k equals 1, another fifth root is the fifth root of 2 times the quantity cosine of 11 pi over 30 plus I times sine of 11 pi over 30. When k equals 2, we get the fifth root of 2 times the quantity cosine of 23 pi over 30 plus I times sine of 23 pi over 30. When k equals 3, we get the fifth root of 2 times the quantity cosine of 7 pi over 6 plus I times sine of 7 pi over 6. Finally, when k equals 4, we get the fifth root of 2 times the quantity cosine of 47 pi over 30 plus I times sine of 47 pi over 30. These are the values of these fifth roots up to 4 significant digits. At this point in the lecture, we will talk a little bit about the geometry of the fifth roots of a complex number using the fifth roots of square root of 3 minus I. The graph on screen shows the first fifth root of square root of 3 minus I, the one with the argument minus pi over 30. Its distance from the origin, or its absolute value, is the fifth root of 2. All the fifth roots of square root of 3 minus I have the same absolute value, so that they all lie on the circle centered at the origin and with radius the fifth root of 2. We add 2 pi over 5, or 1/5 of a full revolution around the origin, to the argument of the first fifth root to get the second fifth root. We again add 2 pi over 5, this time to the argument of the second fifth root to get the third fifth root. Here's the fourth fifth root with an argument of 7 pi over 6. Here's the final fifth root with an argument of 47 pi over 30. And it is 1/5 of a full revolution to get back to the first fifth root. Since by adding 1/5 of a full revolution to the argument of each fifth root, we generate a sequence of 5 regularly spaced points that are equidistant to the origin. In short, the fifth roots of square root of 3 minus I are the vertices of a regular pentagon. To summarize, every non-zero complex number, and this includes non-zero real numbers, has exactly n distinct nth roots if n is a positive integer. And if n is at least 3, then the nth roots of a non-zero complex number are the vertices of a regular n-gon. As another example, here is the plot of the 9 ninth roots of 1 as the vertices of a regular 9-sided polygon or nonagon.